necessarily mean fun for the students, right? Okay, so last time we talked about what the derivative was. Last time we talked about the derivative. Last time we finished up with this definition. We said that f prime of a was equal to the limit as h goes. We didn't actually say this, but I'm saying this. Somebody else provided a different definition of the derivative. We're going to use the h goes to 0, 1, right, for computational reasons. F of a plus h minus f of a over h. Okay. And we pointed out that the reason that you do this is because if this number exists, if f prime of a exists at a, then f is differentiable at a, and f of x is about equal to f of a plus f prime of a times x minus a. I'm going to draw a picture of this time to clarify exactly what I mean by this. So when you're, even this definition of where this limit actually comes from is a picture that looks like this, right? So you've got some function, and you say, I would like to know how this function is behaving at some point, like right here. And so you say, okay, well, if this is a, go this way a little bit to a point, I don't know, h has to come in from the left and the right. So you can imagine a minus h. Go right here. And then this is actually the slope between these 2 points. If this point has coordinates a, maybe I'll make this make more sense by writing it this way so that the picture is more coherent. My argument here is that if this point has coordinates a plus h, comma, f of a plus h, and this has coordinates a, f of a, that the slope between these guys, this line right here, slope of that line, well, that's delta y over delta x, which is f of a plus h minus f of a divided by a plus h minus a, which is f of a plus h minus f of a over h. That's where the definition comes from. Okay. Does anybody know what this is called, by the way? A line that connects 2 points like this? It's a secant line, right? So the secant lines, this is a secant line. And if you let h go to 0, the secant lines approximate the tangent line. As h goes to 0, what happens is this point slides into that one, and the secant lines also slide until in the limit you end up with the tangent line. So the secant lines give you an approximation for the tangent line. So the tangent line is the limit of the secant lines. So of course, none of this works in 2 dimensions or 3, because there's not directions to slide in from. If I'm at a point at a surface and I connect to some other point at a surface, there's a line that connects me, but the tangent line that comes out is just one possible tangent line to the surface. Okay? So what we need to do is we need to somehow try to figure out a way that we can use our one variable. So we want to use one variable ideas. In several variables. I don't know how to generalize this idea. Like this notion of taking a limit as x goes to a of f of a plus h minus f of a over h. This is going to be really complicated in 2 variables because this is supposed to be as h goes to 0. I'm sorry. As h goes to 0. This is going to be hard to compute because this denominator is running away to 0. And remember, when we take these limits, we have to look in all possible, it's not even enough to look in all possible directions. I've got this weird condition where it's like locally the values have to stay close if the inputs stay close, right? This is hard to compute if I replaced all this stuff with vectors. So instead of trying to vectorize this, instead of trying to take this idea and use vectors, the idea that we're going to use is maybe we can take the one variable idea and apply it in two variables. Okay. So the way we're going to do that is with what are called partial derivatives. Don't worry, if it's been a while since you computed a partial derivative, I will remind you how to compute them once we get to that point. Okay, so for the purposes of this section of the class, we are going to restrict our attention to functions that have scalar outputs. So we are going to make the following definition. Let f take a domain in Rn into R. So if I have outputs that are numbers, I call this a scalar valued function. So let f be a scalar valued function. So what we're going to do is we're going to cheat, and we're going to pretend that this function that has n inputs is really a function that has one input. Just pretend. So suppose that we use the notation x1 up to xn for an element of Rn. So I'm going to say x1 is the first slot, x2 is the second slot. These are the naming the variables of the inputs, right? So f is a function of x1, x2, and so on up to xn. So instead of thinking about it as an input of vectors, I'm thinking about it as a pile of n variables that I'm plugging numbers into. Does that make sense? Okay. So the partial function f with respect to xi. So I pick a variable. I can define something called the partial function by doing this. F of xi is equal to f of a1, a2, up to, okay, xi I'm going to leave as a variable. What I'm doing here is I'm saying, put constants in, any constant you want, basically. Put constants in for every other entry except for xi, which stays a variable. Don't worry, I'm going to give examples of it. And okay, so the partial function f with respect to xi is this guy. It's a function of one variable. The only thing that's moving here is the xi variable, and everything else is constant. Where the ai's are constant. This is a way of taking an n variable function and producing a one variable function. So what would that look like? Example, let f of x, y, and z be equal to, I don't know, the square root of x, y, z. That's a scalar valued function of three variables. F, y, the partial function of this with respect to y is equal to the square root of a, y, b, where a and b are constant. I leave one variable that I've chosen as a thing that moves, and everything else I'm thinking of as being constant. The language that gets used in mathematics classes, physics classes, and engineering classes is holding variables constant. In fact, you see this a lot of times in stat and probability classes as well. What we're doing here is, this is called holding x and z constant. We're pretending that we are limiting ourselves to the only motion of the function being in the variable that we've chosen. that make sense? Now, the reason that you want to do that is, as soon as you've got a function of one variable, you can just take its derivative. So partial functions take, we'll put this up here so we remind ourselves what's happening. I start with an f, say x and y, which is equal to, I don't know, x squared plus y squared. And I create a function f of x, which is equal to x squared plus a squared, where this is constant. From two variables to one variable. And the reason for doing it is, if I have one variable functions, I can do one variable calculus to them. Okay, and that's actually how we're going to define what it means to be a partial derivative. The partial derivative of f x1 up to xn is equal to, or is, f prime, I should say the partial derivative of this, let's be more careful, with respect, I have to tell you what I'm taking partial derivative with respect to, which variable. The partial derivative of this n variable function with respect to xi is d by dxi of f of xi, where that is the partial function that you get by with respect to xi, where f of xi is a partial function. That's it. That's what a partial derivative really is. You pretend everything is constant except for one variable, and then you take a derivative. That's easy to say. That's a little bit more difficult to do. But first off, let me give you some notations for what other ways that these things are written. I'll remind you from the past. And certainly I'm not going to get all of these because physics and engineering have their own notations for these. It's common to write dxi of f is equal to d by dxi of fxi. So that's one way of writing it, is with a big capital D and a lowercase letter telling you which variable you're taking with respect to. You guys may remember from earlier classes, partial with respect to xi of f, that means the same thing. That's also the same. My favorite, although it gets confusing when you start taking more than one derivative, f with a little xi written underneath it means the partial derivative of f with respect to xi. So these are pretty much, I guess you could also write, if you wanted to, f prime of xi. All of these symbols mean the same thing. They're used in different contexts. Okay. Of course, symbols don't mean anything if you can't actually compute these things. We should probably do a couple examples just to remind you of how the computation of partial derivatives works. And then we'll talk about what they're used for. Partial derivatives wouldn't be useful unless we could do linear approximations with them. That's where we're headed. Okay, so let's start with an easy one. Let's look at this function right here. I have a function of two variables. I have its partial function with respect to x. So the partial derivative with respect to xi of f of x and y, not even xi, partial derivative with respect to x of f of x and y, is equal to the regular derivative of f of x, where I've taken this function and pretended that everything that is not an x is a constant. D by dx of x squared plus a squared. Yep.
Is it, are we doing it in respect to y? So it's capital Fy in the parentheses?
What do you mean? This is supposed to be.
Is that an x?
No, this is an x here.
Okay.
Yeah. Yeah. Thanks for asking. Okay, and that is 2x. Now, do you need to go through the formalism of replacing all these with different letters? Not if you get used to the idea that all you're doing is pretending that y is a constant. Of course, this is a super easy question. Look, there's not even any interaction between the terms. Let's do something gnarlier. Compute the partial derivative with respect to y of the cosine of x y squared. Okay, so in your head, what you should think is, all right, so what am I actually doing here? I'm creating a partial function and I'm taking its derivative. So I'm taking d by dy of the function that you get by taking the cosine of xy squared, but replacing x with a constant. So if you want, you could just write an a in there if it helps you keep track of what's constant and what's not. And now I'm just doing a regular old one variable derivative, which of course requires that you remember how one variable derivatives work. So this is a chain rule problem. Remember, you're pretending that x is a constant here because you've held x constant. You take a regular derivative of this partial function and you get, okay, I'm going to remind you the chain rule exists. For those of you that maybe haven't thought about this in a couple of years. So, okay, if we're doing this derivative stuff, this is where the computational portion of this class really gets started. We do a lot of computations in here, right? So it's going to look a lot like multivariable calculus, a mixture of multivariable calculus and theory, where we talk about theory and then we apply it with computations. If you find there are ideas from single variable calculus that you don't remember, you've got to come talk to me so we can build those skills back up again, especially for those of you that it's been a while since you've taken the stuff. Okay. So it shouldn't be a surprise that the derivative of this is the derivative of the outside function with the inside unchained times the derivative of the inside function with respect to y, because remember x is a constant, 2ay. And if you want to put it back into being a function of x and y, you would write that this is equal to minus the sine of xy squared times 2xy. You pretended it was constant for a minute so you could compute the derivative, but really this was a function of x and y. Make sense? Okay. These steps are unnecessary if you're comfortable doing partial derivatives. You don't have to write that stuff down. It's just useful to have this, especially when these things start getting more complicated, to keep track of what's constant and what isn't. Okay. How about another? What's the most horrendous computable example I can come up with? Maybe something with 1 over a square root. That's pretty bad. How about f of x, y, and z is equal to 1 over the square root of x squared y z plus z to the third. That's gross.
Is that all under the square root?
All under the square root. See, it's an unfortunate fact of reality that, like, if you actually use mathematics to study the world, there's these inverse square and cube laws running all over the place, and this is actually pretty constant. It shows up all over. We got to take 1 over roots, right? 1 over roots are awful, but super common. What is df dz? Well, if it was up to me, I don't believe that the quotient rule exists. There's actually no such thing as division. There's only multiplication by the multiplicative inverse. And so the very first thing you do when you're taking a derivative of something that involves a quotient is you throw the quotient away and replace it with a nice power expression you can work with instead. After all, we're mathematicians in here. We're not engineers. We don't care about parsing the output. We've got no boss looking over our shoulder that's going to complain if we don't simplify fractions. Besides, that's what computers are for. So df dz is going to be equal to d by dz of this monstrosity. But this time we're going to do it without this sort of crutch of replacing the constant variables. We're just going to remember that we are treating y and x like they are constant when we do this. Now, the inside of this function is moving because it's a function of z, right? This is a function of z in here, and so it does have a derivative. So we're going to take, while power comes down, I'm just not trying to insult anybody. I'm just going to remind people how this works. The power rule says you take the power down and then subtract 1 from it. You multiply by the derivative of the inside by the chain rule. And oh, we'll be doing lots of chain rule here. What is the derivative of the inside? X squared y. Yes. Because x and y were constant. If you find yourself in a situation like this, doing ridiculous product rules because you've got x's and y's running all over the place, be careful, okay? It's really easy when you're doing one of these problems to get pulled into forgetting that these things are constant when you're taking the partial derivative. That's it. I wouldn't go any further than that. I mean, if you want, you could rewrite it as the 1 over the square root of cube of this thing, and it's 1/2 in this denominator, but I don't care. If you're computing for me, you never have to simplify this stuff. You just leave it. It's actually easier to read if you don't simplify it, and you're much less likely to make a mistake if you do that. Okay, so what are partial derivatives for? You know, graphically, this is an illustration. What we've done right here is we're laying out sort of a computation of the partial derivative based on the idea of a partial function, but I haven't really given you an idea of what it is. Graphically, what does a partial derivative represent? So I'm going to show a computer picture in a minute here, but the basic idea, if we think about, I can't draw on more than in three dimensions, so I'm going to assume for a second that f takes R2 into R. It won't surprise you, this will be most of what we study in here, surfaces that look like this. So f is going to take R2 into R. I want you to imagine that what f is doing is that whatever the rule of f is, what it produces is something that looks like this, right? There's some sort of surface that comes out where f takes points down here in the xy plane, and it maps them up to points in this surface, right? This is what a function from R2 into R does. It looks at points in the xy plane and it throws them up into the surface that it generates. We can assume that f is nice for the purposes of this picture. So what the partial derivative is actually doing, if you take something like df dx, or d by dx, let's actually be more precise. If we take d by dx of f of x and y at a point, let's say we're at some point a, b. What we're doing is we're identifying a point a, b down here in the plane. And then we're holding one of the variables constant. Well, which variable are we holding constant in this problem? Y is being held constant, right? So if y is being held constant, that means whatever value of y we had that corresponded to this point, we're holding it constant, which means that there's this line that goes through here of points that have the same y coordinate, right? Everything on this line has the same y coordinate. And when we're computing this derivative, what we're doing is saying, well, take that line and find its graph up here in the surface. So maybe it looks like this. So every point on here, I want you to think of this being something like x, y, f of x and y. I can take that line and calculate the function on that line, and it will turn into the sort of this line strip up in the surface. Does that make sense? I'm just saying that the pink part is like all the x and y values. And I'm saying restrict it to this one line and look at what that line does when you apply f to it. And this is the image of f, of the line under f. What is the partial derivative telling you? Well, it's giving you the slope of this tangent line. The partial derivative with respect to x is telling you what this tangent line is to the curve right here. The way that this particular curve traveling inside the surface, what its tangent line looks like. So the slope of the tangent to the surface at the point AB, f of AB, along the line where, in fact, along the line XB. So that's like a lot of words, but what do I actually mean? Exactly what I drew. You take a line, You look at what it happens to it up here. It's just going to be some curve. It has an actual tangent line. There it is. So the partial derivative is a slope of a tangent line. It's just a specific slope of a tangent line. It's this one in this direction. What is the slope, or what does the other partial derivative give you? Suppose instead we computed, that's an ugly color of chalk, okay. Suppose instead we computed df y. AB. Now what am I computing?
In respect to the y.
So I'm holding x constant, which means I'm sliding in this direction now through that same point, right? Here, I'm thinking of x as being constant. It has a line that travels through the surface. And if I take the partial derivative here, what I'm getting is this tangent line.
What's the pink thing you're drawing? Is that the curve we're looking at, the space?
What's that? The pink, I want you to think, it actually will be clear what's going on here once I put this up on a computer. In fact, maybe I'll do it now so you can visualize it. AB is in the plane down here. That's an X and Y value. The pink thing is supposed to be if you took all of the inputs and you looked at the surface. Like, for example, if you were looking at, these are hard to draw. Imagine that you had a paraboloid. Okay. So through some point in the side of the paraboloid here, if I held it in one direction, remember we did level curves of these things. In one direction, in the X direction, we have this parabola that kind of comes down and looks like this through that point. That point sits on one of these sort of slices of the parabola, right? And on that point, if I took the derivative of this parabola, I would get a tangent line in that direction. On the other hand, there's another parabola that cuts through this way. It goes through the same point. That point is on a parabola that goes this way, and it's on a parabola that cuts through this way. There's two tangent lines. This is getting past my ability to draw coherently. So I actually have a pre-built visualization for this so I can show you guys exactly what's happening. So it will be easier to understand because I anticipated that my ability to describe this was going to be limited by my ability to draw in 3 dimensions. All right. And this is the entire point of all of this, is to be able to do this. So let's go to Math 3D. And this one, I think.
Like a 1-minute free drawing class would be good.
Which one am I in already? Was it this one? Yeah, I mean, the problem is that really to visualize this well, it doesn't just depend on my ability to draw. It depends on my ability to show what's going on to you guys with my drawings. Okay, so this is a total mess. Let me turn this stuff off so you can see exactly what's happening here. So off, 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 off. Okay, so that guy right there, that's a paraboloid, and right? It's a paraboloid. It wraps down like this. So what I'm going to do is I'm going to pick a point on that paraboloid to approximate with partial derivatives. So if you pick this plane right here, that plane corresponds to holding y equals 2 constant for this function. We're saying restrict our attention to only points that have y equals 2 as their y coordinate. What does that look like on the surface? Well, you can see where it intersects, right? This line right here is where everything with coordinate y equals 2, that's what it looks like on the paraboloid. So on the paraboloid, that looks like this. Every one of those points on that curve is down here in the xy plane. I let y equals 2 and x be anything. So that down here is what happens when you take points x comma 2 and take f of them up in the plane. So this parabola is the image of all points that have y equals 2 as their y coordinate. Okay, now, if you took the partial derivative of this function, 9 minus x squared minus y squared, if you took the partial derivative of this function, keeping y constant. That's like taking df dx. And if you compute the tangent line there, you get this. Okay, so I've picked a point and I've evaluated a tangent line at that point. I think the point I chose was 1, 2. X is equal to 1, y equals 2. So x is 1, y is 2 means that z is equal to what, 4? 9 minus 1 minus 4 is 4, right? So what's going on in the background here is I started with the function f of x, y is equal to 9 minus x squared minus y squared. I've picked the point 1, 2 to be my x and y that I'm going to try to compute partial derivatives at. So if I hold y constant to be 2 and I let x run around, this is the tangent line that I get computing the partial derivative at the point 1, 2. Does that make sense? Okay, let's turn that off for a second. If instead I don't pick y equals 2, I let x be constantly equal to 1, I have a parabola cutting the other direction. And I get this other curve. If I take all points 1, y and I feed them into the function, I get this. I'll put the original function back on again too, so you can see where they cross. Both of these parabolas cross through the same point, but this one you get from holding y equal constant, let x run. This one you get from letting x is equal to 1 and letting y be whatever, right? So there's one stripe that goes through in the x direction, one stripe that goes through in the y direction. If you take partial derivatives, you get this. So that point, that line right there is the y partial derivative. This is the x tangent line. And if you see how those two lines, one of which came from the x partial derivative. It's the tangent line with respect to x. This is the tangent line with respect to y. But two lines together make a plane, right? So if you actually construct the plane that those two lines make, you get this. And you should be able to see that that plane is a pretty close approximation for what that parabola looks like, right? I mean, it looks like it agrees with it pretty well right there. So the whole point of partial derivatives is to be able to construct this object. Partial derivatives are going to give us the slope of the red line. Let's get this out of here. It's going to give us the slope of the red line and the slope of the blue line. The partial derivatives actually gave us these tangent lines, and then we're going to use the tangent lines to make the plane that approximates the surface, right? That's what I'm trying to draw with this picture and doing a terrible job at, right? Is that through this point, there's one curve that goes this way, like the red curve that we drew. And there's another curve that goes the other, like perpendicular to it. One curve in the x direction and one curve in the y direction. They both cross through the point. They both have tangent lines, and together those tangent lines make a tangent plane. Okay. Now, in practice, what does this look like for you? Do you need to be able to visualize what's going on when you compute partial derivatives? And the answer is you don't actually need to be able to visualize what's going on. You could just say, oh, I'm going to compute some partial derivatives and then follow a bunch of formulas. And at the end, what's going to fall out is I've got this algorithm and this approximating plane falls out, right? But if you want to understand why this stuff works, which is important, you should understand that what we're doing is we're taking two tangent lines and using them to make a tangent plane. Okay? So that's the point of partial derivatives. The point of partial derivatives is to do this, to be able to write this plane down and use it to approximate the function that you're studying. Okay? In fact, in a lot of science applications, you don't even have the surface. You just have some pile of data points. That's it. You just got a bunch of measured outputs. You have no idea what the function that made the outputs is. But if you're careful, you can still imagine that in small regions, you've got a flat sort of surface and you can work locally like it was flat. So if you have a well-behaved system, even if this is a hairy mess of like measured data, you can still do this. If you've ever done linear regression in Excel, it's essentially what you're doing is constructing one of those guys. Okay, so that's the point of this. So what does it look like in practice? So I guess the idea is Okay. So what are the actual slopes of the vectors? And the idea is that we want to be able to take these computed partial derivatives and actually write down the tangent plane. I need to be able to take the computed partial derivatives, and this wouldn't be useful if I had to work by hand every single time I wanted to write one of these things down, right? In one variable, I always know that I have the function f of a plus f prime of a times x minus a. I want something like that, where I just have the numbers and I can write down the plane. So it turns out to be the case. It turns out to be the case that if you actually write this down, it ends up being the case that plane is defined. What do we need to define a plane? That's a good question. What does it take to write down the equation of a plane? A normal vector and a point. But to get a normal vector, I'm going to need two vectors that are in this plane, right? Where am I going to get two vectors that are in that plane? Well, fortunately, I have these lines. So if I could figure out vectors that pointed in the direction of those lines, I'd be golden. So here's the basic idea. I've got a point AB. Now that's not a point in the surface, that's just inputs A and B. Up here is some point A, B, F of AB. That's up in the surface itself, right? AB is an input, A, B, F of AB is in the plane. If I move in the X direction, there's a curve up here that looks like this, and it has a tangent vector that's sticking out. And the direction of that tangent vector turns out to be 1, 0, F, X of AB. Let's think about what that means for a second. What I'm saying here is if I want to pretend that that's a slope, like the slope of a tangent line, it's not enough to say, I mean, slope doesn't mean anything. Slope means change in y over change in x. So by itself, slope doesn't mean anything. Slope isn't a vector. If I want to think about this as a slope, what I take it to mean is for a unit change in the x direction, I go that slope in the z direction. That's my change in z. A unit change in the x direction induces this much change in the z direction. Does that make sense or no? And this is kind of abstract here, but the idea is a partial derivative can be used to find the vector that determines that tangent line, if I think of this as a slope. So one vector in the plane, v1, equal to 1, 0, fx, ab. Another vector that's in the tangent plane you would get if you did the other direction. If you move this way in the y direction, then you've got another curve that goes out like this, and you have another tangent vector. What is the direction of this tangent vector? Well, now I've got a unit change in the y direction. So I move 1 unit in the y direction, no units in the x direction, and I've got a slope that tells me how much my z change is. I should get v2 is equal to 0, 1 fy ab. If I move from that point 1 unit in the y direction, the slope that I change is fyab. All right, let me reiterate here.
How do we know to start out 0, 0?
What do you mean start out 0, 0? So what does slope actually mean is the question, right? So when you look at m in a one variable case and you think dy dx, what you mean here is change in y per unit change in x. Right, so in a one variable derivative, it's change in y per unit change in x. For a partial derivative, fxab means unit change in z, unit change in height. Sorry, not unit change, change in height. Change in z, that is change in height of the surface, per unit change. Well, what is moving, x or y? For a partial derivative in x, what's changing? X is changing per unit change in x. And that means for every unit change in x and no change in y, go that far in the z direction. V2 says for every no change in x and unit change in y, go this far in the z direction. So this is measuring how you move if you restrict yourself to going in the x direction, and this is measuring how you move if you restrict yourself to traveling in the y direction. Okay. Now, because you have nothing better to do than compute normal vectors, to get the equation of, we almost have what we need to have the equation of a plane now. We have a point, which is a, b, f of ab. We know that point is in the surface. There it is right there. That's the point. We have two vectors in the plane. We have a v1 that is equal to 1, 0, fx ab. We have a v2 that is 0, 1, y ab. If I only change in the x direction, I look like I'm doing this. If I only change in the y direction, I look like I'm doing that. If only I had a normal vector. If only. So if you grind out the computation, it turns out to be the case that v1 cross v2, if you take those two vectors and cross them to get the normal to the plane, just turns out to be minus fx minus fy 1. So if you cross those two vectors, this is what you get. If you're bored tonight, you want to test me, you are welcome to cross those two vectors and see that this is what comes out. Now, the reason it's so simple is because there are these zeros in here, right? And this is the reason why we're using coordinate directions, and so that these don't interact with each other. The x direction and the y direction are perpendicular, and that means the cross is really nice. In theory, you could do this with any two vectors to the point, but that would suck. And that means you have the normal vector n. N is equal to minus fx, minus fy, 1. And so finally, using the fact that you have a normal vector and a point, you can write down that the tangent plane, if it exists, the tangent plane has the formula n dot p naught b is, oh, that's kind of dissatisfying. So instead, let's actually compute this and write z is equal to f of ab. Say here, f of ab plus fx ab minus a plus fy ab. And this bad boy right here, that's the equation of a tangent plane. And in fact, you should recognize that this is very similar to the definition of the tangent line from one variable, right? In one variable, remember, we say y is about equal to f of a plus f prime of a times x minus a. Close to the point x equals a, this line is about equal to the graph. Here, we fix an f and ab. This is the same. It tells us where to start the line. This tells us the slope in both the x and the y directions. And this gives us a way of measuring how far away we've moved from the initial point. This is basically the same equation. Okay. Here's the complication. It's kind of obnoxious that this complication exists. There are many functions for which this is actually not true. Tangent planes don't always exist. So like good applied mathematicians, we say, why would we ever deal with one where it doesn't? So we're going to give it a special name. If f from Rn into R, so say x, Rn into R has a tangent plane at every x, then we say f is differentiable. Notice, it is not enough. It's not enough to say that the partial derivatives exist, right? It's not enough to say the partial derivatives exist. We must go further than that. The partial derivatives existing and being computable do not guarantee that this is true. I'll show an example next time of a function that doesn't have this be the case, right? Basically what happens is the partial derivatives could disappear and be zero. And then the surface could pinch to a point or a cusp. And then how do you write a tangent plane at a cusp? And the answer is you don't. It's not differentiable there. You can imagine a surface that had this shape. Where this comes to a point, this is easy to draw a function for. That's not going to have a tangent plane at this point. But it could be the case the partial derivatives are defined here. All right, so our goal for next time is going to be, how on earth are we going to tell when we're allowed to do this? Which are the nice functions that we actually want to work with? Now you are set up at this point to go and do anything involved in the homework involving computing partial derivatives. I urge you to leap in. Right? Just to start working on it. Compute some partial derivatives, compute some tangent planes, and then we'll talk about how you know they exist and what the nice functions are when we're done. All right. Thanks for your attention, guys. I'll see you tomorrow.
Professor, I just want to ask, are you planning on posting this lecture on the agenda?
Is that not up yet? Maybe I just didn't publish it. Yes, absolutely. All of the lectures will always be posted. I have them all recorded. If I have not posted it yet, it is because